Hey everyone, today we're going to be looking at formal charge. This is going to be building off of what we looked at the other day with Lewis structures and putting them into the correct form in covalent molecules. Um, so just kind of drawing on some past knowledge that we've looked at, I'd like you to just pause the video and try this first example on your own. So draw the molecule of HON in as many possible ways as you can while satisfying all of the rules that we've learned so far. So really the main rule that we want to make sure we're following is keeping a nice stable octet. So pause the video now and draw as many different structures of HON as you can. Okay, so some possible ones that you could come up with are H N with a lone pair there and a double bond to our oxygen. Hydrogen's happy, 2 valence electrons. 2, 4, 6, 8. Our nitrogen is happy, 2, 4, 6, 8. Our oxygen is happy. Hydrogen is offering 1, nitrogen is offering 5, and our oxygen is offering 6. So we have 12 valence electrons to work with. Have we satisfied that? 2, 4, 6, 8, 10, 12. Awesome. Another way that you could write this molecule is H, now with our O in the middle with a lone pair there, and a double bond onto our nitrogen with 2 lone pairs. 2 valence electrons for our hydrogen is happy, 2, 4, 6, 8. Oxygen's happy, 2, 4, 6, 8 for our nitrogen. 2, 4, 6, 8, 10, 12. So we've used all of our available valence electrons. So both of these are potential molecules for HON. What we're going to look at today is which one is actually the more correct version. So which one, if you're asked to draw out the molecule of HON in its Lewis structure, which one would you actually want to use? So sometimes molecules can be drawn in more than one way, as we just looked at. So really the ultimate question is, how do we know which is the best way to do it? What this starts to look at is this is looking at something new known as formal charge. So you're probably asking yourself, what does that even mean? Well, we're going to look at what formal charge is. So formal charge is looking at the number of valence electrons that an atom has and then subtracting the number of covalent bonds that it is touching, as well as subtracting the total number of electrons in lone pairs. And what this is going to give you is this is going to give you the formal charge of each atom within a covalent molecule. So what it means by formal charge is what is the charge over that individual atom within the full molecule. And we always want to have the lowest possible charge to make sure that it is the most stable structure that we can put together. So the most stable molecule is always going to be where the formal charges are the lowest. So let's stop just talking about what this is and let's actually practice it. Okay. So one thing we always need to remember is this equation that is boxed here for us. So the number of valence electrons, the number of covalent bonds, and the number of lone electrons. This is going to be used to determine the formal charge of each atom. So not of the entire molecule, but of each atom within the molecule. So if we're looking at HONO2, and we have our two different ways that it can be drawn out, we need to look at which one is more stable. So if I was to ask you to draw the most stable form of HNO2, which one do you need to actually draw out, and how would you know? So this is where we can start to look at formal charge. So remembering that our equation that we're going to be using is our number of valence electrons minus our number of covalent bonds minus our number of electrons in lone pairs. I apologize for how terrible the writing is. Still getting used to this stylus. So let's take a look at this to try to determine which of these two structures is more stable. Well, let's start looking at hydrogen. We have one valence electron available with hydrogen. We have one covalent bond, and we have no electrons in lone pairs. So the formal charge over this entire atom is 0. If we're looking at our first oxygen, we have 6 valence electrons available. We have 3 covalent bonds, and we have 2 electrons in a lone pair, which gives us a formal charge over our first oxygen of +1. If we're looking at our nitrogen here, we've got 5 valence electrons available, we've got 3 covalent bonds, and we have 2 lone pair electrons, which gives us a formal charge of 0. If we look at our second oxygen, we have 6 available valence electrons, we have 1 covalent bond, and we have 6 electrons in lone pairs, which gives us a total formal charge of -1. So if we were to draw out the formal charges of this entire structure, we don't need to include anything that's 0. If it's 0, then you just don't write anything. But if I was to show the charge of the different atoms within this molecule, we'd have a plus and a minus. So those offset, and it gives us a charge over the entire structure of 0. That's why we can actually draw this and it's going to be stable. But we need to actually compare it now to our other possible structure of HNO2. As we can have either the double bond, here, or we can have the double bond here. So let's look at the formal charges now of our second structure. So hydrogen, again, we have 1 valence electron, we have 1 covalent bond, and we have 0 lone pair electrons, which gives us a formal charge of 0. If we're looking at our first oxygen, we have 6 valence electrons available, we have 2 covalent bonds, and we have 4 lone pair electrons, which gives us a formal charge of 0. Oh, this is already looking a little bit better. If we're looking at our nitrogen here, we have 5 valence electrons, 3 covalent bonds, and 2 lone pair electrons to give us a formal charge of 0. And then our second oxygen, we have 6 valence electrons, we have 2 paired in covalent bonds, and we have 4 valence electrons. So that gives us a charge of 0. Whoa! So our formal charges over this structure is 0 on each atom. So if you were to take a nice educated guess of which one is more stable, which would you choose? As we're all geniuses in this class, obviously this one. Yes, over here we have a plus and a minus that equals out to be a net charge of 0, but here we have no charge over any of our atoms, so this is actually the more stable of the two. This is a challenge for you. I want to see if you can figure this out, so pause the video and give this a go. You're going to draw the Lewis structure of sulfuric acid, so the most stable form of sulfuric acid. So pause the video and give that a try. So I'm sure everyone tried the challenge. They got the correct answer because you were all just the smartest individuals known to man. And we have come up with the correct structure being this one over here. As if you were actually draw out the formal charge on each individual atom, with the structure on the left, we've got some zeros around our hydrogen and our oxygen, but we also have some +2, -1, -1, as well as some zeros. Again, the whole net charge over the over the molecule itself is 0, but if you compare it to our other structure, the charges, the formal charges across all the atoms are individually 0, which makes this more stable. Here, there's just too many formal charges, right? And the formal charges on each atom over here are 0, making this more stable than the other. So we've looked so far at just molecules that do not have a charge on them, so they're not potentially polyatomic. So if we have a charge on a molecule, you have to make sure that you add or subtract electrons depending on that charge. So if we have a positive charge, we are taking away electrons. If we have a negative charge, we are adding electrons to it. Just like we do with our ionic compounds and our Lewis structures, if you gain or lose electrons to create a bond, you need to show what the charge is on that actual molecule. So in this case, we have to include in square brackets and indicate what that charge is. Is it a positive or is it a negative? So if we're looking at, say, ammonia, that positive is telling us that we have lost an electron. So when we actually do our charge over the entire molecule, we need to show that there is a charge on it, being positive as we have lost an electron. So this can actually still react. There's going to be some instances where both structures that you draw have equal charge. So one is not actually more stable than the other. And this is where we get into our new topic of resonance structures. So resonance structures are the different ways that a molecule can be drawn that have the same formal charge across the entire molecule. So one is actually not more correct than the other. In this case, you have to draw all the structures, as you cannot just draw one because it does not exist as that one structure in nature. It actually can flip-flop between the 2 or 3 or potentially 4 different structures. So this also brings into the idea of fractional bonds, and we'll start taking a look at that in a bit as we move on. As I just said, to show these molecules with the greatest accuracy, you have to show all of the different possibilities. So if I was to ask you a question to draw all the potential structures of a molecule and it has potentially resonance, you must show all the possibilities. And we're going to start looking now at these resonance structures. So if we're to look at this example here of sulfuric acid, we can see that especially with this, the double bond can exist around each of our oxygens that's bound to our central sulfur, meaning that each one has got the same formal charge no matter what, but it can exist in 3 different places. You have to then show all 3 different molecular combinations to be completely right when showing this. And we're going to start to get into some examples of this now. So if you're to draw out NO2, and we know through experimental data that the bond strength of each N to O bond is the same in magnitude between the strength of an NO and an NO2, NO single bonded and an NO double bonded. That is to say that between each N and O there exists 1.5 bonds. So what does this mean? How can it be that between an N and O in NO2 minus we have a bond of 1.5? You can't have half of a bond. So I'm going to draw this out and go through it with you to kind of make you understand what that actually means. So we've got our molecule of NO2 minus. N has got 5 valence electrons to offer. Oxygen has got 6. We've got 2 of them though, which gives us 12. So we're dealing with 17. But we also have a charge over our molecule, and it's a negative charge, so we have to add 1 more electron. So we have 18 valence electrons in total to work with. Since we have 1 nitrogen and 2 oxygens, nitrogen is going to be our central atom. Next thing we have to do is connect our two other atoms to our central atom, we have used up 4 electrons so far in those bonds. So we now have 14 to work with. If I put our remaining valence electrons into this molecule, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, we now can total them up and see if this is a happy structure. So we've got 2, 4, 6, 8, 2, 4, 6, 8 around each oxygen, so they're happy. 2, 4, 6. So our 2 oxygens have stable, happy octets. Our nitrogen is not stable and happy. So what we can actually do is bring one of these pairs down and create a double bond with our nitrogen. So now we have 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around our nitrogen, and 2, 4, 6, 8 around this oxygen. So that's happy. We can also draw this structure having a double bond on this side. So what we can say is that NO2- has resonance. It exists as 2 stable structures. What this means of 1.5 bonds is, if we're actually looking at it, in both structures we have 1 double bond and 1 single bond. So to say that the bond between each N and O exists as 1.5 bonds is that in both structures we have a double and a single existing on each oxygen and nitrogen, meaning that we have 1.5 bonds. As we do not have 2 double, we don't have 2 single, we have 1 double, 1 single, making it 1.5 bonds between the N and the O due to resonance. We looked at this example up above in the notes, but if you were to draw out SO3 2-, so if we were to look at this and draw out all the different possible structures of SO3 2-, we have 3 different possible orientations of this molecule, with the double bond existing on different oxygens. Because of this, we can say that the bond between oxygen and sulfur is 1.3. The reason it is 1.3 is it's existing between 3 different possible orientations. So we have 2 singles and 1 double, but that double bond is switching between oxygens. So we have to draw 3 different structures to be entirely correct when showing the proper structure of SO3 2-. If you don't draw all 3, you're not showing all the possible stable orientations of this molecule. So I'm going to leave you with this question of trying to draw the proper Lewis structure orientation of HPO3 2-. So pause the video now and try this on your own. So I'm sure that everyone got these 3 possible orientations of HPO3 2-. So we have our hydrogen, is stable and happy. We've got our oxygen having a double bond either on oxygen 1, oxygen 2, or oxygen 3. You can see that our formal charge is denoted by the negative here. Lastly, in terms of symmetry, so when you actually start drawing these out, molecules want to be symmetrical. The more symmetry it has, the more stable it is. As we all know in chemistry, everything wants to be stable and happy. So if it is not symmetrical, it's going to be less stable. Molecules tend to have a central atom. Okay, so they don't exist in big long chains. They're usually going to be existing with the central atom. And that central atom can change. You usually have to look at, what are you looking at? Organic compounds are going to always have carbon in the middle, but that can change. You may not be looking at a organic compound, so you might have to look at something else and look at the bond nature of that atom itself. So how many bonds can it create with it? How many valence electrons can it donate? So if we're looking at POCl3, there's two different ways that you can draw this out, and then we can draw in the formal charges of each. So it can exist with our phosphorus in the middle, with our 3 chlorines existing around it, and our oxygen up at top. And then we can also have a double bond